Alright, so we have learned about the time complexity, we have learned about the space complexity, we have learned about different equations, we have learned the master theorem. Now let us look into all the popular data structures and algorithms and find their typical time and space complexities and their typical use cases. So let's start with arrays and strings. Typically, when you access an element in an array or a string, it takes constant time because we are using the index operator and we are directly going to a particular index in the array. If you are searching in an array, then searching takes order of n time if the array is not sorted. So if the array is not sorted, then the searching will be linear search. And if the array is sorted, then we can apply binary search also. If we apply linear search, then the time taken is order of n. And in case the array is sorted and we are able to apply binary search, then the time taken will be order of log of n. In both the cases, the extra memory will be constant. If you want to insert an element in the array or you want to delete an element from the array, then typically it will take order of n time because you may end up traversing the entire array to find the right place to insert or to find the element to delete. And if you have an array, let's say your array is 1, 2, 3, 4, 5, and there is enough space at the end. Let us assume that we want to insert 7 in between 2 and 3. So if you want to insert 7 between 2 and 3, then you need to shift all of these elements by one position. So shifting will also take some time. That's why insertion and deletion typically takes order of n time. If you look at the algorithms on the array, there is a sliding window algorithm, there are two-pointer approach, and there is prefix sum. We'll see them later. Next data structure is a hash table. So hash table is used in both HashMap and HashSet. You can relate it with dictionary in Python. HashMap or HashSet is a data structure where insert, delete, and search, all of these operations takes constant time. So whenever we are using HashMap, we consider the time complexity to be constant. But we must also remember that in worst case, these time complexities can be order of n. If your hash function is so bad that all the keys are having collision at the same place, then it will be a worst case for HashMap and that will take order of n time. Here we have mentioned the space complexity of insert operation as order of n because if you are inserting n elements, then it will take order of n space. Unless there is a worst case type of collision, typically HashMap and HashSet takes constant time to insert, search, and delete. Also, if you are dealing with frequency of a number in your question, then most typically you will end up using HashMap. So HashMap and HashSet are typically used when we are counting the frequency of elements in the given data structure. The stack data structure is a last in first out data structure where elements are deleted in the opposite order of their insertion. So if we are first pushing 5, then 8, then 3, then the element will be popped first will be 3. So first 3 will be popped, then 8 will be popped, then 5 will be popped. Pop refers to the delete operation, push refers to the insert operation, and peek is an operation where we are accessing the topmost element of the stack without actually deleting it. Stack data structure is typically used in questions related to parentheses. Whenever you see balanced parentheses or count the parentheses in any question, think of using a stack. Also, if you want to find next greater element for all the elements in the given array, in that case also you will end up using stack. Queue is a data structure where elements are inserted and deleted in, first out order. So it is first come, first serve. The elements are inserted from one end and deleted from the other end. So if 5 comes, then 5 will be inserted. If 8 comes, then 8 will be inserted. If 3 comes, then 3 will be inserted. Now, if you want to delete an element, then 5 will be deleted because it is a first in, first out. 5 was the first element which was inserted in the queue. Therefore, 5 will be the first element which will be deleted from the queue. The two ends of the queue are typically the front end and the rear end. And typically the insertion happens at the rear end and deletion happens from the front end. If you have a special implementation of the queue where you can insert from both rear and front, and you can also delete an element from both front and rear, then that is called a DQ. The typical time complexity of inserting or deleting an element in a queue is constant. So is the time complexity of pushing or popping an element from a stack. The biggest application of queue is that queue is used in the BFS algorithm, breadth first search algorithm, or the level order traversal algorithm in a binary tree. Next data structure is a linked list. We know that in a linked list, we keep a pointer to the first node. First node has data. Let's say the data is 5 and first node contains the address of second node. Second node has its own data and it contains the address of the third node. Third node contains its own data and also contains address of the fourth node. Like this, we keep on going node after node, and the last node contains null. So every node has a data and a pointer to the next node. If we want to access any element in the linked list, then we cannot jump directly to that element like we did in arrays. Therefore, the time complexity of accessing any element in the linked list is order of n. Here, when we say the time complexity, we are talking about the worst case time complexity. If you want to access the first element of the linked list, then obviously this time complexity will be constant. But this is the best case time complexity of accessing an element. In the worst case, when you are accessing the last element of the list, the time complexity will be big O of n. Because we only have the address of the first node, and to go to the last element, we have to hop each and every node in the list. A popular algorithm in linked list is to have two pointers, slow pointer and fast pointer, where slow pointer is moving at a slower speed while fast pointer is moving at a faster speed. Let's say slow pointer is going to the next node while the fast pointer is jumping two nodes at a time. When the fast pointer reaches the end of the list, the slow pointer will be at the middle of the list. This combination of slow and fast pointers is used in multiple questions in linked list. For example, if you want to check whether a loop exists in the linked list or not, you will use slow and fast pointer. Typically, if you want to reverse a linked list, the time taken to reverse the linked list will be big O of n. If you want to insert an element at the head of the list, which means that you want to make that element as the first element of the list, then the time taken will be constant. The time taken to insert any element in between the list or at the end of the list will be big O of n. So insertion and deletion typically takes big O of n time if we are inserting in between or at the end of the list. But they will take constant time if you are inserting at the head of the list. After linked list, the next data structure is the tree data structure, which is extremely important. In a tree data structure, we have a node that contains one data and two pointers. The two pointers points to the left subtree and right subtree respectively. A binary tree is a two-dimensional data structure and it is hierarchical in nature, where every node has two children, the left child and the right child. If the first level has one node, the next level has two nodes, the third level will have four nodes, the next level will have 8 nodes, and so on, provided the tree is complete. Typically, traversing the tree takes order of n time, whether it is using recursion, which means DFS, or using level order traversal, which means BFS. And we have also seen that when we are traversing the tree using pre-order traversal, in-order traversal, or post-order traversal, which means that when we are traversing the tree using recursion or DFS, then the extra memory will be equal to the height of the tree. In case if you want to traverse the tree using BFS, then the extra memory will be equal to the width of the tree, which is typically order of n. If the tree is a binary search tree, then in a binary search tree, you either traverse the left or the right of the tree, but not both of them. Therefore, at every level, you are only accessing one node. So if you have a tree like this, 5, 3, 10, then 2, 4, 6, 12. And if you want to search 6 in this tree, you compare 6 with 5. Because 6 is greater than 5, we will discard all the elements in the left subtree, because all of these elements in the left subtree are also less than 5. So we move to the right child and compare 6 with 10. Because 6 is less than 10, we discard the right side of 10 and move to the left child. At every level, at the first level, we are accessing only one node. At the second level, we are accessing only one node. At the third level also, we are accessing only one node. Because we are accessing only one node at every level, therefore, the total time taken will be equal to number of levels, which is equal to log n if the tree is balanced. Which means whether you are inserting in a binary search tree or deleting from a binary search tree or searching in a binary search tree, the time taken for all of these operations is equal to the height of binary search tree, which is equal to log n if the tree is balanced. If it is unbalanced, then the height of the tree can go up to order of n. But this is only when the tree is unbalanced. Next data structure is a heap data structure. Now heap is a very interesting data structure because physically heap is an array, but logically heap is visualized as a tree. Heap is visualized as almost complete binary tree. And if it is almost complete binary tree, automatically it will be balanced. Now heap is nothing but a priority queue. And we know that in a queue, there are two operations. Either you can insert an element in a queue or you can remove an element from the queue. For a heap, these two operations will take log n time. Whether you are inserting an element in a queue, whether you are inserting an element in a heap or you are deleting an element from a heap, both of these operations will take order of log n time. Peak means that you are only accessing the topmost element of the heap without deleting it. That takes constant time because the topmost element is present at the first position in the array. If you are given an interview problem and while solving that interview problem, you end up finding either the minimum or the maximum element again and again, then you must think of using the heap. If you are finding the minimum element again and again, then you should think of using a min heap. And if you are finding the maximum element again and again, then you should think of using the max heap. Heap is used in situations where we are finding the maximum or the minimum element again and again. Like in case of Dijkstra's algorithm where we are finding the shortest route. So while finding the shortest route in a graph, we pick the edges in their increasing order. We pick the minimum edge out of all the given edges, remove that edge from the heap, and then find the minimum edge out of the remaining edges. It means that we are finding the minimum edge again and again. Therefore, we should be using heap in that case. The typical use of Trie data structure is in the implementation of dictionary. If we want to store all the words in a dictionary and the length of each word is L, then the total time taken to insert that word in a trie will be order of L. If you want to insert cat in a trie data structure, then this will take order of 3 time because there are 3 characters in this word. If you want to insert catch, then this will take order of 5 time because there are 5 characters, and so on. The time taken is big O of L, where L is the length of the word that we are trying to insert or search in the trie data structure. And obviously because we are storing all the words and total number of words are n, the total memory taken will be n into length of each word, which is big O of n into L. Next is the graph data structure. Most of the students find the graph data structure difficult because they do not look at the implementation of the graph. They study graph only in theory. If you implement the graph using adjacency list, then it will take order of v plus e time, where v is the number of vertices in the graph and e is the number of edges in the graph. But if you are using the adjacency matrix representation of the graph, it will take order of v square space because we will be storing the edges in a 2-dimensional array of order v cross v. So the space taken will be order of v square. The typical algorithm to traverse graph is BFS and DFS. So DFS is nothing but recursion and BFS is nothing but level order traversal. And for a graph, both of these algorithms take order of v plus e time, where v is the number of vertices and e is the number of edges. And the extra memory taken in both the cases is order of v, because we will be storing the vertices in a visited hash set. Also, recursion will have its own call stack that will take some space, and level order traversal will be using queue that will also take some space. A typical application of BFS is to find the shortest route, and a typical application of DFS is the topological sorting. You may also come across questions where we are either detecting cycle in a graph or we are finding the number of connected components in a graph, like the island problem of a 2-dimensional matrix. Because the underlying algorithm used in these problems is either DFS or BFS, therefore the corresponding time and space complexity will be according to the underlying algorithm. Now let's come to the sorting algorithms. There are so many sorting algorithms like bubble sort, selection sort, insertion sort, merge sort, quick sort, heap sort, radix sort, counting sort, and other sorting algorithms. Broadly, we can divide these sorting algorithms in 2 buckets. First is the set of sorting algorithms which are comparison sorting algorithm, and second is the set of algorithms which are non-comparison sorting algorithms. Comparison sorting algorithms are those sorting algorithms where elements of array are compared before sorting, and non-comparison sorting algorithms are those where we sort the array without actually comparing the elements of the array. An example of non-comparison sorting algorithm is counting sort. Another example is radix sort. Another example is bucket sort. So all of these are non-comparison sorting algorithms. Example of comparison sorting algorithm is bubble sort, selection sort, quick sort, merge sort, heap sort. These are comparison sorting algorithms. If you are given nothing about the nature of elements in an array, then in most of the cases you will end up using a comparison sorting algorithm. And the best comparison sorting algorithm will have a time complexity of n log n in the worst case. Both merge sort, quick sort, both of these have the time complexity of n log n. Even heap sort has the time complexity of n log n. But because the constant factor of heap sort is higher than both merge sort and quick sort, therefore in most of the cases we will end up using either merge sort or quick sort to sort the array. We know that the worst case time complexity of quicksort is order of n square, but the typical consideration is that quicksort takes n log n time in the worst case, and this is possible when the pivot selection of quicksort is random. So if you have an implementation of quicksort where the pivot is randomly selected, then theoretically you can say that this implementation will take n log n time in the worst case. So even though the worst case time complexity of quicksort is n square, during the interviews we will always say that quicksort takes n log n time in the worst case. Now let's come to searching algorithms. Typically there are two searching algorithms, linear search and binary search. We know that linear search takes linear time, which is order of n, and binary search takes order of log n time. In binary search, we divide the array in two parts and we only consider one part for the next iteration and the second part is discarded. So either the left side is discarded or the right side is discarded depending on whether the element at mid is less than or greater than the value that we are searching in this array. There is one more way of searching an element, and that is to not search an element in the given data structure. Let's say the given data structure is a graph and it takes a lot of time to search in the graph. So a faster way of searching the elements of a graph is to put all of these elements in a hash map. Put all of these elements in either a hash map or a hash set. And then we can search in this hash map or hash set data structure instead of searching in the graph. So that will improve the search complexity and make it equal to order of 1. Because now we are not searching in the original data structure. Instead, we are searching in a hash map which contains all the values of the original data structure. So it will reduce the time to search, but obviously it will increase the memory complexity because now we are duplicating the entire data structure. Therefore, the extra space will be order of n. We can also think about some algorithmic patterns like sliding window, two-pointer approach. A sliding window typically has 2 pointers, the start of the window and the end of the window, and this window moves forward in the array. So start is moving at its own pace, end is moving at its own pace. Sometimes the width of this window is fixed. Sometimes the window is dynamic in size, so it keeps on increasing and decreasing. But typically the sliding window problems have linear time solution. In most of the cases, the extra space is also constant, but sometimes we end up taking extra space which is equal to the width of the window. So here k is the width of the window, the distance between start and end. Sliding window is also a two-pointer approach, but you can also say that two-pointer approach is when you have start and end. Start is moving forward and end is moving backward. So this is an approach that we used in the partition logic of quicksort. This approach also takes order of n time and constant extra space. We use this approach to check whether the given array is a palindrome or not. Let's say we are given an array like this, A, B, C, C, B, A. Keep a low pointer at the beginning and a high pointer at the end. Elements at low and high are compared because both of them are equal. So we do low plus plus and high minus minus. Then we compare these two elements because these two elements are also equal. So we again do low plus plus and high minus minus. We keep on increasing low and decreasing high until high crosses low. So when high goes beyond low, then we say that now since we have considered the entire array, we stop the loop. Therefore, the total time taken is order of n because every element is considered only once, either by the low pointer or by the high pointer. Backtracking is another way of problem solving where we move forward and then come back. The typical implementation of backtracking algorithms is using recursion, and in some cases the time complexity can go up to exponential time complexity. Next is dynamic programming. A dynamic programming problem is first solved using recursion. If you have a recursive solution that is taking a lot of time, typically an exponential time, and we have overlapping subproblems in this recursion, which means that we are solving the same subproblem again and again, then we optimize this recursion using dynamic programming. In dynamic programming, we maintain a table which is usually either a one-dimensional array or a two-dimensional array to store the solution of smaller problems so that we can use those solutions to find the solution of the larger problem. If there is only one variable in the dynamic programming solution, we will use a one-dimensional array. And if there are two variables in the dynamic programming problem, we will use a two-dimensional array. So if we are using a two-dimensional array, then the time complexity will be order of n square. And if we are using a one-dimensional array, then the time complexity will be order of n. If it is a one-dimensional array, typically the time complexity is order of n and the extra space is also order of n. But if we are dealing with two variables in the solution, then we typically use a two-dimensional array. And if the range of first variable is 1 to n and the range of second variable is from 1 to m, then the time taken will be order of n into m. And we use a two-dimensional array of order n cross m. Therefore, the extra space will also be order of n into m. Obviously, what I am saying here is a general guideline and it may not represent the time and space complexity of all the dynamic programming problems. Sometimes in the interview, we are asked questions related to bit manipulation. If you are performing bitwise AND or bitwise or bitwise XOR, then these operations takes constant time. If you want to set a particular bit in the binary representation of a number, or you want to reset a particular bit, or you want to flip or toggle a particular bit, or you want to get a particular bit, all of these operations takes constant time. So manipulating a particular bit in the binary representation of a number is constant time operation. And for that we use masking. You will find many coding interview problems which also use XOR operation. So if you are using XOR operation in an array, obviously it will take order of n time because you will be XORing all the elements of the array. But one XOR operation will take constant time. This was a very short summary of time and space complexities with respect to all the popular data structures and algorithms. We should remember that during the interview, when we talk about the time and space complexity, we should be as objective as possible. So for example, we should not say that the function is fast, because fast can't be measured. Whenever you are talking about the speed, you should talk in terms of time complexity, that how fast is the function. So the function takes order of n time or order of n square time or order of n cube time, whether it is exponential time complexity. So those things are measurable times and measurable time complexities. Similarly, when we talk about the space, we should not be talking about approximations. We should be talking in terms of the asymptotic space complexity. We can say that the space is constant, big O of 1. In many questions, there is a trade-off between time and space. So there is one implementation which is taking order of n square time and it is taking constant extra space. But there is another solution of the same problem which takes order of n time, but this solution also takes order of n space. We cannot say that the first solution is better or the second solution is better, because the first solution is taking more time but it is taking less space, whereas the second solution is taking less time but it is taking more space. We must apprise the interviewer about the trade-offs between multiple solutions that we have in our mind. This was all about time and space complexities. I genuinely hope that this course helped you. I wish you all the best.